Greetings, welcome to this new video about Thevenin's theorem. In this video, I will demonstrate the application of Thevenin's theorem through step-by-step example explanation. By following along carefully, you will gain a clear understanding of how to apply Thevenin's theorem to solve practical problems. Let's dive in and begin with the solve the problem number 19. Let's consider the galvanometer circuit consisting of 4 resistors labeled R1 through R4 as well as one independent voltage source Vs. Rm represents the galvanometer resistance. The question now is to find the current Ig through the galvanometer using Thevenin's theorem. Let's move on to the solution. By applying the Thevenin's theorem between terminals A and B, we can replace this circuit with the voltage source in series with the resistor, which will be denoted as VTH and RTH. In our example, RTH is connected with in series with Rm, which plays the role of the load. I will start first with the determination of the Thevenin's resistance. This step can be done by disconnecting Rm and removing all independent sources in the circuit. That means the voltage source Vs will be replaced by a short circuit. The Thevenin's resistance represents the equivalent resistance between terminals A and B when Rm is disconnected. That means RTH is equal to the parallel combination of R1 and R2 connected in series with the parallel combination of R3 and R4. Therefore, RTH can be calculated using the following formula. R1 times R2 over R1 plus R2 plus R3 times R4 over R3 plus R4. And if we replace the resistors with their numerical values, we obtain RTH is equal to 990 ohms. After finishing the determination of the Thevenin's resistance, we proceed to calculate the Thevenin's voltage. The Thevenin's voltage is basically the open circuit voltage calculated between terminals A and B. To find the open circuit voltage, VOC, I will apply the voltage division principle and Kirchhoff's voltage law. Using the voltage division principle, we can write the voltage V1 across the resistor R2 is equal to R2 over R1 plus R2 times Vs. And if we replace the resistors and the voltage with their numerical values, we obtain V1 is equal to 55 volt. And the voltage V2 across the resistor R4 is equal to R4 over R3 plus R4 times Vs. And if we replace R3, R4 and Vs with their numerical values, we obtain V2 is equal to 132 volt. Now, by applying Kirchhoff's voltage law in loop 1, we can write negative V1 plus VOC plus V2 is equal to 0. And if we replace V1 and V2 with their numerical values, we obtain VOC is equal to negative 77 volt. That means VTH is equal to negative 77 volt. The current through the galvanometer is equal to VTH over RTH plus Rm. And if we replace Rm, RTH and VTH with their numerical values, we obtain Ig is equal to negative 74.76 milliamps. After completing the calculations, I perform a simulation using SPICE to verify our results. Now let's proceed to the SPICE environment. Here our networks drawn in SPICE simulator. This is the original circuit, and this is the Thevenin's equivalent circuit between terminals A and B. I connect here a non-parameter in order to measure the current Ig in the original circuit, and here a non-parameter in order to measure the current Ig in the Thevenin's equivalent circuit. Let's move on to analysis. DC analysis, calculate nodal voltage. We can see here that the current Ig is equal to negative 74.76 milliamps in the original circuit and is equal to negative 74.76 milliamps in the Thevenin's equivalent circuit. From the simulation, it becomes clear that the current Ig is similar when using both the original circuit and the Thevenin's equivalent circuit. This similarity validates the correctness of our calculations. Alright, thank you for watching this video. If you have any question, do not hesitate to contact me by email or leave a comment under this video and I will answer you as soon as possible. If you like this video, don't forget to subscribe and share. See you next time in another video about Thevenin's theorem. Take care and bye bye.